Next up, we're thrilled to welcome Kevin Scott. Kevin Scott is Executive Vice President of Technology and Research and the CTO of Microsoft. He is an innovative leader driving the technical vision to achieve Microsoft's mission and is passionate about creating technologies that benefit everyone. He focuses on helping make the company an exceptional place for engineers, developers, and researchers to work and learn. Scott's 20-year career in technology spans both academia and industry as researcher, engineer, and leader. Prior to joining Microsoft, he was Senior Vice President of Engineering and Operations at LinkedIn, where he helped build the technology and engineering team and led the company through an IPO and 6 years of rapid growth. Scott is the host of the podcast Behind the Tech and authored the book Reprogramming the American Dream, which explores how AI can be realistically used to serve the interests of everyone and not just the privileged few. He has received a Google Founders Award, an Intel PhD Fellowship, and an ACM Recognition of Service Award. Scott holds an MS in Computer Science from Wake Forest University, a BS in Computer Science from Lynchburg College, and has completed most of his PhD in Computer Science at the University of Virginia. Kevin is joined by Alex Wang, CEO and founder at Scale. Alex, over to you.
Awesome. Thank you so much for sitting down with us today, Kevin. I'm super excited to be chatting with you.
Yeah, I'm really glad to be back again.
First of all, welcome back to Transform and excited to do another conversation. I think that, we're going to talk all about AI. You've been writing and speaking about AI for quite some time, and obviously in your book, Reprogramming the American Dream, you predict that AI will radically disrupt economics and employment for generations to come. So maybe first, just to start out with, what was kind of your first aha moment with AI? I know you've been working with it for some time now, and when did you kind of first realize that it had incredible potential to change the way we live and work?
Yeah, I've been working in machine learning now for a while. I think the first machine learning program I wrote was in 2004. Like really, really long while, I guess, relatively speaking. And back then, I wouldn't have expected to see as much progress as we've seen over the past 17 years. Like, what I was doing was relatively arcane. Like, I was building a bunch of classification technology for some things in Google's ad system, and eventually using a bag of machine learning techniques for doing very technical things like predicting the CTR for an ad. But what I think we've seen, especially with the deep learning revolution since 2012 or so, and maybe more so over the past few years, is that the machine learning technologies are becoming more broadly applicable. And I think this is really accelerated over the past 2 to 3 years. And I think things are finally at the point where you just see a broader and broader range of people using machine learning to solve their problems every day, which means that machine learning has a greater and greater impact on what's happening in the world. And it's not just ranking the ranking search results or ranking the content that you have in your social media feed. It is helping scientists solve problems that they have in their particular domain. It's helping us manage global pandemics, and increasingly it is packaging machine learning up in ways where lots and lots of developers can easily use the technologies. So things like the OpenAI API, Azure Cognitive Services, Codex, GitHub Copilot. There are just so many ways now that developers can actually pick these tools up where they don't have to do what I did 17 years ago and sort of stare at a stack of graduate textbooks and spend 6 months writing a bunch of low-level C++ code to get a single thing to work.
Yeah, totally. And I think that Microsoft and OpenAI have partnered on a bunch of really exciting tools. You mentioned Copilot and Codex and all that stuff more recently. When we had our last conversation in March, we were kind of you shared your thoughts on kind of the potential of self-supervised models as well as the transformer networks that had recently come out. Maybe take us quickly on a quick tour of what you think are some of the most important advancements since then, whether they be sort of applications of that technology, like with Codex, with additional optimizations, Codex and Copilot, and what you think the potential implications of those advancements are.
Yeah, I think the core things that we talked about last time have continued to proceed apace. So the self-supervised models themselves, the larger they scale, they are becoming better at performing the tasks that we know they can perform, and they're also admitting a broader range of tasks. So at each decade of scale, it seems you can do more and more with these models, and we've gotten to the point where you can really start thinking about these models themselves. Some people call them pre-trained models, like we call them platform models at Microsoft. Stanford just published a really good survey paper, although it's like 160-something pages, so it's almost like a monograph that talks about the field, and I think they're calling them foundation models. But the general idea is that not everyone should have to replicate these big models from scratch, and you can sort of use them as software engineering objects that you can take what someone else has trained and then either fine-tuned or, like, using no fine-tuning whatsoever, go solve a whole bunch of problems that the original model builders didn't think about at all. And so that's really exciting. Like, that can unlock a ton of creativity, and this broadening of what things are useful for has definitely been on display over the past 6 months. So the OpenAI Codex model and its use in GitHub Copilot is a pretty good example of this. So you take a model that started off being good at a bunch of natural language tasks, and turns out you can make it be good at artificial language tasks like programming. So that's super exciting, but we've also seen these self-supervised learning techniques applied in different areas. So the same set of techniques are being applied to vision, and we've had a whole bunch of breakthrough vision results over the past 6 months where you're building these pre-trained models for computer vision. We're seeing multimodal models where you're training in multiple domains simultaneously. So text and vision, for instance, and then maybe even the most exciting things that are happening along these lines are things where we're applying the technique to things like graphs. So researchers at MSR published an interesting paper on this idea called graph formers, which is a way to do self-supervised learning on graph-structured data. And the particular thing that they're using these pre-trained models for is in molecular dynamics and solving simulation problems around molecules and solving molecular structures like protein folding. And like that's super exciting. And I will say that the second interesting thing that has just continued to happen and that's accelerating and picking up pace in general over the past 6 months is the number of places that people are using either these self-supervised platform models or using techniques from reinforcement learning to solve problems in the sciences, where you have maybe a simulation problem or a combinatorial optimization problem where it is very, very computationally expensive to get to very accurate solutions to the problem. In the case of combinatorial optimization, most of these interesting things are NP-hard problems, and in the case of simulation problems, you usually have this trade-off of complexity and time scale versus or time steps in your simulation versus the overall amount of compute you're spending or the amount of compute time that a calculation takes. And we've been able in a whole bunch of places to use machine learning to learn something about the structure of these problems where you can dramatically accelerate the performance of simulations. So interesting paper from some PhD students at Caltech on using this bag of techniques for solving Navier-Stokes flow equations for airfoil design. There's just been some very interesting stuff happening in molecular dynamics, and the stunning thing here is that when you apply these techniques, things aren't getting 10% better or 50% better, twice as good. They're getting orders of magnitude better. This Caltech result, which is emblematic of like a pattern that I've seen hundreds of times now, got 1,000x performance improvement by building what they're calling neural operator for their simulation system for Navier-Stokes. So it's just sort of an incredibly exciting thing as more people figure out how to use these techniques.
Yeah, totally. I mean, one mental model I have here, and I'm curious what you think about, is like there's in a lot of these real world problems, if you think about like the ages of human sort of science building or knowledge building, we kind of had math and physics as our primary analysis tool, and so that allowed us to get certain levels of performance and to do things really well. But like now, deep learning and machine learning is almost this like new kind of analysis tool that is like better at finding weak correlations in data, better at finding sort of like these subtle things that frankly even human brains aren't that great at identifying, and you can use it as an analysis tool like to make significant progress on things that maybe with previous analysis tools we would say are just like we know are really, really hard, like the simulations, the sort of biological molecular dynamics problems, and all these things that you just referenced.
Yeah, I completely agree with that. It is almost, you can think of it almost like an adjunct to mathematics and numerical optimization in a certain sense. I mean, with these combinatorial optimization problems, like it's just been obvious for a while that I don't want to offend any of my computer scientist friends who work on combinatorial optimization, but usually these things get solved with approximation algorithms, and the approximation algorithms involve a bunch of heuristics, and the heuristics are not elegant. So they are just, and again, I'm going to end up offending a whole bunch of people, but like they're almost like hacks where you sort of take a human understanding of some of this complexity or shortcuts that you can find based on your understanding of the problem domain, and you use that to try to accelerate solution of the problems. And what we're seeing is exactly what you said. You can use machine learning systems to really understand or model the complexity of some of these problem domains in ways that are just really hard to do with heuristics or even with analytical modeling. And it doesn't mean that you throw your mathematics away and that you don't care about elegance and that you're okay not understanding what these things do. It's just it is the next step along this path that we were already on to dealing with a world that is really, really, really complicated, and you just sort of need these tools to make progress.
100%. One thing, a lot of the community is pretty focused on AGI as kind of like this like great end state, but obviously there's lots of applications along the way that have already changed people's lives, like AI personal assistants, or obviously all the improvements to ranking systems online, and there's been now improvements that have seeped into the medical industry, seeped into the financial services industry, et cetera, et cetera. And so there's lots of pretty exciting advancements that are like real tangible advancements that are happening. What are some transformative use cases for AI that you think are kind of around the corner? One of them, in my opinion, is Copilot that GitHub released with Codex, like accelerating the innovation loop of writing code is something that's like pretty exciting and will have a lot of downstream effects. But I'm curious what other use cases you're excited about.
Yeah, I mean, the way that I have started thinking about these tools is they are here to assist us in doing cognitive work. We have lots and lots and lots of tools that we've been using for the entire history of the human race to assist us with doing physical work. And even in the 17th or 18th century, we came up with a set of physical theories and engineering principles around, what physical work actually is, and what the science of that is. And like we're very early days in having the same thing for cognitive work. But Copilot's it's a good example. No one is going to argue that programming is not cognitive work. You're sitting down and sort of using your understanding of a machine and your understanding of the problem that you're trying to solve and your understanding of this like very complicated set of tools that we have for solving programming problems, and you're trying to wrestle with all of that complexity to go write a piece of code that does what you intend it to do. And so Copilot is a tool for helping people do this sort of cognitive work. One of the things that's been especially helpful for me doing is I am at this point what I would call an occasional programmer. So I'm not, thank goodness, I'm not on any sort of production critical path with the code that I write, but I still write code because it's a great way for me to think. But I am at a point in my coding life where the ecosystem of APIs and tools, it's just so hard that I find myself sitting in front of an editor or a notebook or something, and I'm just constantly doing searches for what's the right pandas invocation to slice this data in this particular way. And so the point of Copilot is to help you manage some of that complexity so you can be more productive at programming. It is absolutely not about it's not about removing the need that the world has for programmers. It's almost a recognition that the world has a profound need for programmers, and that we want to take our precious few programmers that we have and help them be more productive at their work. And then I think, the next step beyond that, which is really exciting, is sort of widening the aperture on who can be a programmer. You and I may have chatted about this before, but like this is one of the more exciting things to me about machine learning in general is it may help, and like I think Copilot is a very big step along this path to change what it means to be a programmer from, you have to be an expert on all of these different very complicated things in order to write any code at all, to like providing some sort of entry point for people where they can write a little bit of code by trying to teach the computer what to do, not trying to tell it what it must do in very arcane language. So that I think is super, super exciting, especially in a world where we don't have enough programmers to build all of the software that the world needs. And you touched on a couple of other like really interesting things. So, these breakthroughs that we're having with these simulation systems where we're getting orders of magnitude improvement in performance, like that's not just, oh, gee, we can do a little bit more. It sort of transforms what you're able to do. I'm really excited about what's happening in drug discovery and protein design right now. So, we already saw using these bag of techniques allowed us to come up with structures that are protein structures that have super high binding affinity for the receptor binding domain on SARS coronavirus 2. But like the thing that's even more exciting than that is being able to model the interactions that a synthetic protein like that might have inside of the entire human proteome. And like that is computationally infeasible right now. So even if you had solved structures for the entire human proteome, like being able to do all of those pairwise interactions would be prohibitively complicated, or prohibitively expensive. But if you had a system that makes the computation of these interactions in a simulation environment 1 million times faster than they were before, like all of a sudden you can do just extraordinarily interesting things.
Totally. Yeah. And one thing that you touched on there, which I think is AI has the ability to really level the playing field and democratize access to technology over time, which is something that's incredibly exciting. There's sort of the famous quote, which is "the future is here. It's just it isn't equally distributed yet." And I think that for a lot of us in the tech world, we obviously get very excited because we see the future. We see these large scale machine learning systems. We see what the potential is. But I do think that one thing that is maybe underappreciated is the degree to which this technology is going to ultimately democratize the future. And so maybe I'm curious to hear your thoughts a little bit on how that happens. I know this is something that you've written a lot about in the past. You grew up in West Virginia and rural America, and it's something that I know you think a lot about, not only from a technological sense, but also a sociological sense. So I'm curious how you think this will play out.
Well, I think this whole notion of models as platforms, of APIs, of computing systems that allow you to sort of explain in human language an effect you're trying to accomplish versus having to learn a programming language and computer science in order to be able to get a computer to do something programmatically that a programmer hasn't already coded for you. It is really exactly this step towards democratization. And like the way that we will know that we're being successful here is how many new businesses are being created because they have access to these technologies, because they're able to build a brand new thing that wasn't possible before because they can get access to one of these APIs, or because they have their scientists and their engineers figuring out how to apply these new techniques to problems they've been working on for a while. And I think we really do have both an opportunity and a responsibility to make sure that as we make these platforms available, that they're available to everyone. I'm just a firm believer that we at tech companies and Silicon Valley startups can't possibly imagine all of the interesting and valuable things that can be done with technology, and that we need not just tens or hundreds of thousands of people who work at these companies to be building things, but we need hundreds of millions or billions of people able to harness the power of these machines, where they get to decide what the machines do, not have someone decide on their behalf what the machine can do for them. And I really do think we have that opportunity right now. Like these tools are actually open. Like you can be an entrepreneur in rural America, and like this is even changed for the better over the past year and a half with the pandemic. Like you can be anywhere and be an entrepreneur. You don't need a team of data scientists or AI engineers sitting, right next to you in, some place like Gladys, Virginia, where I grew up, which, has a few hundred people. Like you could start a business, collaborating with people using video conferencing technology and the internet, wherever you all are in the world, and running your applications on a cloud and using all of these open source tools and these APIs that are available to you. I think it's really exciting, and like part of what we have to do is just show people that it's possible.
Yeah, totally. What I want to drill in on one very specific component of kind of the democratization of AI, which is one of the things that a lot of these new methods require is they require huge amounts of compute. And over time, I think it's been increasingly obvious that there's sort of like almost an AI compute bottleneck where, we just need more and more compute to train these great algorithms. How do you think the AI community in the United States, or just even globally, should think about addressing this sort of like compute bottleneck where the current resources and funding are highly skewed in favor of a small subset of the community or the industry where there's access to huge amounts of compute resources. But ideally, we want obviously this technology to be accessible to all.
Yeah. So I completely agree that this is a huge problem, but before I get into like why and what we should do about it, like I will start by saying there is some good news, like the fact that you do have models that operate as platforms and companies that are willing to put APIs around these models and to like provide access to the means that not everyone necessarily needs to have a multi-$100 million AI supercomputer to train a model from scratch. And even if we at Microsoft look at how our machine learning work is progressing over time, we're going from this mode where every team at the company has, for maybe the past 10 years, thought about, all right, it's my team and my data scientists and my data and my model and my experimentation framework and my feedback loop and my ML ops to deploy into production and my product iteration process, where you're basically building everything. And now, with these platform models, we're able to, for natural language, give folks big models that they then are fine-tuning and deploying. And if you look at what we were spending, just in terms of computation and data wrangling across the entire breadth of like all of these separate machine learning efforts, like it's actually, even though we're spending an enormous amount of resources training bigger models, we're spending less money training smaller models. So it is. I believe in the long run, especially given how fast we're able to improve the efficiency of the training process, that this is going to net out and be less expensive over the long run. But you are absolutely right that like in the moment right now, if you want to build a 10 trillion parameter model, there just aren't that many places in the world that have enough compute in one place where you can go build such a thing. And so I think it is really important in the United States for our policymakers to think about how we can provide a lot more funding to universities and independent public research labs so they can go build similar sorts of things and help there be a diversity of thought about the systems architecture aspects of this, because it's super complicated what we're doing. And yeah, I think Microsoft and Google and Facebook and some of the other folks who are building these really big models are publishing a lot and sharing some of what they're doing, but it's not the same as if you had all of academia being able to actively participate in the whole process. So the thing also that I'm hopeful for is I don't know that it's always going to be this expensive in terms of compute. So we've had these step function breakthroughs in the efficiency of training and the efficiency of inference over the past handful of years, where I think there are just a huge amount of gains to be had. And like one of the intuitive reasons that everyone should believe that is you might have a megawatt cluster for training a really big model. You have a training cluster sitting between your ears that burns tens of watts of power. So there is a biological proof point that training can be much more efficient than it is right now. And so what we're doing at Microsoft is we're investing super heavily in scale up, because like it's an engineering problem at this point. Like we know how to. It's complicated, but it's you know how you go do the work and you spend the money, and like this thing is going to scale. But like we're also investing fairly heavily in alternatives to the prevailing paradigm, because we believe that it can be better.
I actually like, to your point on American policy. One thing that I'm really curious to get your thoughts on. So, the United States, we kind of led the world on internet standards and 4G standards. And then right now we're kind of in this painful battle with China on 5G standards. I know this is something that Microsoft actually sort of stepped in on, did a huge amount of work on, working to make sure that the United States had viable alternatives when it came to 5G. Something that's underreported, underappreciated, and actually frankly kind of misunderstood is the growing battle on AI standards between the United States and China. What do you think that we can be doing as a country, or the U.S. policymakers can be doing to ensure that we don't end up in another 5G situation, but where we really come out ahead on standards and governance for AI?
Yeah, I think the place where it starts is having good public-private partnerships on these things, and I know that we have been pretty heavily involved in the National Security Council's Commission on AI, and Eric Horvitz, who is our chief scientific officer and like one of the luminaries in AI machine learning, was one of the co-authors of that document, along with his colleagues and peers from Google and a bunch of other places. So it is the case that I think we have a robust conversation happening between practitioners in industry, in academia, and in government about where AI is headed and what some of the policies are. I think there's a bunch of things that we should be thinking about in terms of national competitiveness and just sort of policies and incentives that we're putting in place. Just because we have and it's not just the U.S. I think it's sort of, you have this notion of liberal democratic nations have a particular ethos around what it is they want technology to do for their citizens, and how it is they want their citizens accordingly to participate in the development of the technology. And I think by and large that has served us extraordinarily well over the past century and arguably beyond. So I think it's really important for all of us to pay attention and to continue having these conversations and to invest. And I would argue that we need to be spending more of our public resources in building a healthy set of foundations for AI, starting with making sure that we've got good silicon investments. Again, you hit the nail on the head that we are compute constrained right now, and compute starts with compute. So we need to make sure that we can build the chips that we need to to ensure that we can build these AI supercomputers. It's super important that we continue to have robust pipelines of diverse students who are getting computer science degrees and PhDs in computer science and focusing and specializing in artificial intelligence and machine learning. And then I think I write about this in my book, but with the Apollo program, we spent something on the order of 2% of GDP every year for 10 years to get to the moon. And, it was such a transformative thing for society that now you literally, we talk about moonshots, as a super ambitious thing that we all want to do. And everybody's got a moonshot. The moonshot came from the Apollo program, where we literally taught the world what high ambition looks like. But in a sense, going to the moon was super arbitrary. But what it took to get to the moon was not. And it gave us our entire defense industrial base. It gave us our aerospace industry. It gave us just an unimaginable acceleration and boost in technology. And I think we could do the same thing by spending an even smaller percentage of GDP than 2% on machine learning and picking as our next moonshot something that is a problem we really need solved, affordable health care for everyone, or a set of solutions to global warming, or this is the one that I think about a lot, the demographic inversion that we're in the middle of right now, where we have a very rapidly aging population in almost the entirety of the industrialized world, including China, Japan, and Korea, where if we don't have massive technological improvements to productivity and to problems like healthcare, like we're going to be in trouble, because you're going to have more retired people and aging and in declining health, and you have workers to do all of the work that they were doing before, and so it's sort of like a 2-for-1. Like, who's going to help take care of the aging, and like who's going to do the work that they no longer are doing because they're not in the workforce. And like that, in my mind, like that's a thing that we have to have more AI, machine learning, and like the things that will come from that to help solve.
I think one of the things that I always love when I talk to you is like you're definitely a very big AI optimist, and I think actually what's even more true is you probably look towards AI as one of the few answers to some of these like big societal questions that we have. What do you think? You kind of alluded to this before, which is like, hey, Codex and Copilot, which uses Codex, is not the end of programming as the end of programming at all. It may be the end of programming as we know it today, and might up level the activity and might make us more efficient. How do you think about this in a general sense? Like, how do you think we can best prepare as a country for the ways in which work will change and evolve as a result of AI adoption? And how do you think what does that mean for people within the AI community, for what we can be doing to minimize any negative externalities of that change?
Yeah, I think to answer the last question, I think all of us who are developing AI technologies ought to be thinking about both the good and the bad of what you can do with these tools as we develop them. And it's impossible to imagine all the bad in the same way that it's impossible to imagine all of the good. But you at least have to have some sort of grounding in both directions. Like, you can't just be an optimist without being a little bit of a pessimist as well. I think the conversations that we're having right now about about adverse effects and safety and ethics and bias and I think these conversations by and large have been just extraordinarily valuable in trying to get us centered. But I do want to make sure that we don't lose the optimism as we are focused on the bad stuff that potentially can happen, because I really do believe that we need these tools in the world, because we've got a bunch of very, very hard problems that are going to be difficult to solve without them. And it's not like I'm happy with whatever way it is we ultimately solve the problems, but we sort of have to solve them. And as an engineer and someone whose entire life has been about looking at things that are broken and imagining how you go fix them, these are very, very promising looking tools. I mean, I think the biggest thing that we can do to prepare people for what's coming is just make sure that we all who are in the field are being better teachers for everyone about where the technology is and where we see it going. I probably mentioned this to you before as well, but yeah, we have Neil deGrasse Tyson, whom I love, goes on late night TV to talk to the American public about astrophysics, which is great. Like, we need more scientific literacy in the population at large. But we don't really have that corollary for computer scientists and engineers, or, like, God forbid, artificial intelligence practitioners who are, like, really trying to make that effort to go out and talk to the public about what's going on and what they should be hopeful about and what they should be concerned about. And the last thing that I will say is I think that in addition to all of us taking on like those two responsibilities, like, thinking about both the good and the bad, and like doing more, talking to, just folks everywhere about, what it is that we're doing to try to get them more involved and inspired, is I do think these tools, as they become democratized, will need people to be literate or numerate and on several dimensions of technology, but like it also re-emphasizes our need to focus on like what is essentially human, like our creativity, our ability to communicate with one another, our ability to reach consensus, to build these stable social equilibria. So, like, I think that's an important thing that we got to educate our kids for. I tell, the teachers and the administrators at my kids' school this all the time. It's like they fret about, test taking, and like, are we preparing these kids to, to get perfect scores on standardized tests? And I'm like, well, the robots already can get perfect scores on standardized tests. It's like that's not the thing that is going to distinguish our children in the future from, and prepare them to actually use the tools to go do the creative things that only they can do. So I think just us focusing a little bit on what makes us human, and it is not doing repetitive cognitive work any more than we lament the existence of the forklift because it can lift more weight than a human being. Like, we're not going to, in 10 years from now, lament the existence of a machine learning system that can assist us with cognitive work. We're going to think, oh, the crap that this thing is doing is like, that was miserable stuff that I never wanted to do in the first place.
Yep, totally. I want to actually kind of go back to Moonshots, because this is always a fun conversation that we have. Obviously, I think to your point, the Apollo project was this incredible goal, this incredible mission that created all these positive externalities, all this good. And I think there's been more recent examples of like maybe similar kinds of instances where there's sort of some sort of like public-private university partnership around goals that inspire a lot of innovation. For example, the DARPA Urban Driving Challenge kind of created the modern autonomous vehicle industry, which is super exciting. What are some other moonshots that, we have a lot of really bright people, really talented people in the audience today. What are some other moonshots that you'd encourage people to be thinking about, or that you want to see more people be doing?
So I think security would be a very good one. How to use these tools, machine learning and otherwise, to help defend all of us from malicious uses of the technology and the infrastructure that is in the world. I would love to see folks thinking about a grand challenge in manufacturing and making. One of the things that we're seeing right now as a consequence of the pandemic is we have just a complete and utter global snarl in our supply chains. And so what do we need to do to robustify all of that stuff so that we can, continue to build all of the things that society needs, and maybe even build more of those things more cheaply and more flexibly than we have been. I think there's certainly a grand challenge on health in general, and like that's a very broad category. It's everything from how can you have good expert companionship for the elderly, for instance. There are places in rural Maine, for instance, where for no amount of money can you pay for the amount of elder care that is needed in that population, and like that's just sort of a canary in the coal mine for what's about to come. So, how do you use technology to help with elder care, so the elderly can live a healthy, dignified life. There's probably a grand challenge on drug discovery that would be outstanding. So like we know that there are an infinity of molecules out there that we can use for good therapeutic effect. And so like we've hopefully, well, some of us at least have seen the miracle that are these mRNA vaccines that are just now have revolutionized immunology, but that those same technologies and ones that are even more sophisticated can maybe the things that are going to help us with cure cancer finally and to deal with neurodegenerative disease. And there, yeah, I mean, look, I could go on for another half an hour here.
Yeah, no, I think the drug discovery one is such a great example, and it really speaks to when we talk about like what's the potential optimization. It's so massive, right? Like I remember if you look at the early coverage on how long is it going to take us to develop and launch a vaccine for COVID, the original estimates were like a decade, and then with the recent advancement in biotechnology, we can move so much faster, and that's not even with AI. The potential for us to just get better at all these things is massive. I kind of want to end again. I think we're both big AI optimists, and so it can be fun to kind of think long term. As the quotes usually go. We overestimate what we can do in a year, but underestimate what we can do in 10 years. What do you kind of think of our good goals for the AI community to set over the next decade? Like, what do you think, looking back, if we don't accomplish, we're going to be pretty disappointed in ourselves if we didn't make like X happen with AI?
I think we should have objectives around real democratization of the technology. If the bulk of the value that gets created from AI accrues to a handful of companies in the West Coast of the United States, like that is a failure. I think we need to have objectives around, how do you measure real human benefit? So, it's like all of the folks who are practitioners at your event are like understand that these AI systems are very good at optimizing objective functions, and like we just need to choose objective functions that really take into consideration human benefit and sort of social good. I think we need real innovation in the fundamental algorithms here, because like we have a set of things that are working, but like obviously they are very inefficient relative to where they could be. So I don't know. I mean, maybe those three things I think in my mind are like they are literally top of mind for me. Like it's not even 10 years. Like if we can't get those things right in the next 2 years, we're gonna have big problems.
Yeah, no, I love it. Well, with that, thank you so much for taking the time, Kevin. This was a super fun conversation. We covered a lot of ground, and thanks for coming back to Transform.
Yeah, thanks for having me.